Engineering education typically relies on linear memorization in isolated lecture halls, but mapping the relationships between current sustainability problems and historical solutions reveals an organic, interconnected network of applied science. The National Education Policy 2020 mandates a restructure of this model across Indian higher education frameworks. This policy removes the reliance on lecture-based instruction inherited from colonial-era educational systems. Institutions are now adopting the ethnoSTEAM framework, which applies rigorous science and mathematics to specific cultural and socio-ecological contexts. Students study Indian knowledge systems as a rigorous archive of empirical science. This archive encompasses historically tested methodologies in metallurgy, fluid dynamics, and mechanics. Design thinking serves as the primary method for connecting these historical observations to modern problem-solving. By reverse engineering the engineering feats of antiquity, students extract data that can be tested against modern materials engineering requirements. This digital map organizes the new curriculum into 3 technical domains: design thinking, ethnoengineering, and ecological architecture. At the University of Mumbai, the first-year engineering syllabus has been restructured to implement these domains. The first semester shifts from traditional teacher-led lectures to a learner-centric model focused on active inquiry. The immediate introduction of design thinking requires students to solve open-ended problems, a departure from the formula-heavy training common in secondary school. The syllabus integrates vocational skill practices and open electives, allowing students to explore the intersections of science, commerce, and the arts. This foundational year uses a lower credit burden to orient students toward continuous evaluation and interdisciplinary research. This structure trains students to approach engineering as an iterative process, which is required to navigate emerging technology trends. The ethnoengineering module follows a similar approach. This coursework focuses on hard science case studies, beginning with ancient Indian metallurgy. Students examine the specific iron extracting techniques perfected by tribal communities centuries ago. Analysis of the Wootz steel lattice reveals a highly engineered atomic structure with rust-resistant properties. This structural integrity supported extensive export networks stretching from India to the Mediterranean world. The module also investigates the material science behind ancient bronze work. Ancient bronze casting required precise temperature control and the use of wax molds, ensuring molten metal succeeded in filling a complex cavity without structural defects. In the creation of Aran-Mula mirrors, specific metallic proportions were calculated to produce highly reflective, distortion-free surfaces. These methods align with the physics principles taught in modern precision casting and photonics. Studying indigenous metallurgy provides modern engineers with empirical templates for developing advanced alloys. These same principles are applied to ecological architecture and sustainable mechanics. The IKS 201 module focuses on traditional ecological practices and decentralized water management. The architectural geometry of Indian stepwells demonstrates an advanced understanding of fluid dynamics and drainage. These subterranean structures used thermal mass to create passive cooling systems. Beyond fluid dynamics, students analyze the vector mechanics used in monumental construction. The Konark Sun Temple serves as a primary case study in large-scale load-bearing structural engineering. Ancient manuscripts associated with the site record details of stone-lifting mechanisms and the workforce required to move these multi-ton loads. Analyzing these feats requires students to apply foundational physics within specific historical and ecological constraints. The curriculum is designed to prevent these historical studies from becoming static subjects. This is achieved through project-based learning, which replaces passive classroom lectures. In a flipped classroom model, students complete theoretical research before starting physical projects. Students use modern laser sensors to map the precise geometry of ancient sites, extracting raw data for digital analysis. Mandatory site visits to forts and research museums allow for direct interaction with historical engineering solutions. Students must then produce analytical reports comparing indigenous mechanics to global scientific systems. This field-based approach converts historical observation into actionable data for modern engineering design. Integrating these technical domains produces a holistic profile for the modern Indian engineer. The ethnoSTEAM framework maintains technical rigor by applying science and mathematics to culturally significant problems. This approach makes hard science locally relevant. Historical geometry from sites like stepwells can directly inform the development of modern green architecture. Identifying the empirical basis of traditional practices removes historical biases from technical education. It prepares engineers who possess both cultural roots and technological fluency. This repository of historically tested empirical wisdom provides the baseline for developing sustainable global solutions.